Question 8 is on kinematics, and in part A we're asked to find the velocity of a particle whose velocity is given with this function here. So we're asked to find the velocity of the particle when t equals 1. So that is just v of 1. So if we substitute in, we're going to have 1 squared minus 4, so negative 3 cubed, and that is going to give us negative 27 meters per second. In part B then, we are asked to find the acceleration of the particle. So the key relationship to recognize here is that the acceleration t is equal to the derivative of the velocity. So in essence here what we've got to do is differentiate this function, and as we noted earlier, given that this is a composite function, we're going to have to use the chain rule to differentiate this. So we're going to start off by differentiating the outside of the brackets. So this would be 3t squared minus 4 to the power 2, and then we're going to multiply that by the derivative of what's inside the brackets, which is going to be 2t, and we will end up there with 6t multiplied by t squared minus 4 to the power 2. In part C, there are a couple of different ways that you could do this. One way you could do it is by recognizing that the acceleration will be at a maximum when the rate of change of acceleration is 0, so by differentiating this, but you'll see that it's only worth a couple of marks, and this is on the calculator paper, so you can use your calculator. So for the easiest way to do this is actually to graph it, and if you graph it, it looks like this. So you can see from the graph then that there is a readily identifiable maximum point here where t equals 0.89, and we've got an acceleration of 55. However, in this instance, the question asks us to find the time at which the maximum acceleration is reached, and we're given a domain up here of t between 0 and 3. So although we have got a local maximum here of 55 at t equals 0.89, we're not specifically asked for the local. It doesn't say local here, it's just the maximum. So we can interpret that then as the global maximum. So we would ordinarily need to check both extrema, but we can see straight away on the graph here that when t equals 0, it's clearly got a value of 0. So all we need to then is check for when t equals 3. So if we have a look, if we substitute in or we look on the graph, we can see that actually when t equals 3, the acceleration will be up here somewhere at 125. So whilst there is a local maximum at t equals 0.89, we are in effect here in the question asked for the global maximum, which will be when t equals 3, and that will give you an acceleration of 125, but we're not actually asked for the acceleration, it's just the maximum time, so time equals 3. The other approach that you could have used to solve this problem would have been to have taken the acceleration and then find the derivative of the acceleration. So if you found the derivative of the acceleration, that would have told you the maximum or minimum points of the acceleration, because you could have set the derivative of acceleration equal to 0 and solved. But again, that would have given you the local max or min, so you still would have had to have tested the extrema as well. But that's just another way you could have done it using calculus rather than using the graph. But as I said, using the graph here is the much more straightforward way of solving this.